Welcome to WhiteboardDoodles, the channel where we simplify tech-related concepts using whiteboard animations. In today's video, we will be exploring the basics of cryptography. In our digital world where almost everything works electronically, the need for securing and protecting our data has become crucial. That's where cryptography comes in. But what exactly does it mean, and how does it work? Stick around to learn more about the backbone of secure communication. First, let's look at what cryptography is. Cryptography is the science and art of securing information by converting it into an unreadable format, known as ciphertext, to protect it from unauthorized access. This process involves techniques such as encryption, where data is encoded, and decryption, where it is decoded back to its original form. Cryptography ensures the confidentiality, integrity, and authenticity of data, making it essential for secure communication in our digital world. It underpins many security protocols and applications, from online banking to private messaging, by safeguarding sensitive information against cyber threats. Now that we know what cryptography is, let's take a look at the key concepts related to it. These include encryption and decryption, keys, hash functions, digital signatures, certificate authorities, SSL/TLS protocols, and public key infrastructure, or PKI for short. These concepts are the building blocks of cryptography, forming the foundation for secure communication and data protection in the digital world. Grasping these ideas is essential for understanding how cryptography keeps our information safe. Let's examine each one of them individually. We'll first look at encryption and decryption. Encryption involves converting plaintext or readable data into ciphertext, an unreadable format using an algorithm and an encryption key. This ensures that only authorized parties with the corresponding decryption key can access the original information. Decryption, on the other hand, is the reverse process where ciphertext is converted back into plaintext using a decryption key. These processes are crucial for protecting sensitive data, ensuring privacy, and securing communications across various platforms and applications. That said, encryption can be divided into two main types: symmetric and asymmetric encryption. Both have their pros and cons and should be applied depending on the requirements. Symmetric encryption is a type of encryption where the same key is used for both encrypting and decrypting data. This method is known for its simplicity and efficiency, making it ideal for securing large amounts of data quickly. In symmetric encryption, the key must be kept secret, as anyone with access to it can both encrypt and decrypt the information. Common algorithms used in symmetric encryption include the Advanced Encryption Standard, AES, and the Data Encryption Standard, DES. While highly effective, symmetric encryption poses a key distribution challenge, securely sharing the key between parties. If the key is compromised, the data can be easily decrypted. Despite this, it remains a cornerstone of cryptographic practices, widely used in applications like securing file transfers, encrypting databases, and protecting data in transit. Now let's quickly look at asymmetric encryption. Asymmetric encryption, also known as public key cryptography, employs a pair of keys for encrypting and decrypting data. These keys are mathematically related but distinct. The public key is widely distributed and used for encryption, while the private key remains confidential and is used for decryption. This dual key system addresses the key distribution challenge of symmetric encryption, enhancing security in digital communications. Asymmetric encryption enables secure exchange of sensitive information over insecure channels, such as the Internet, without the need for prior key exchange. Popular algorithms include RSA and elliptic curve cryptography, ECC. While slower than symmetric encryption due to complex computations, asymmetric encryption plays a crucial role in securing online transactions, digital signatures, and establishing secure communication channels between parties who have never met or exchanged keys before. Now let's briefly look at keys. As we mentioned earlier when discussing encryption, keys are fundamental components that dictate the transformation of data during encryption and decryption processes. These keys are essentially strings of characters that work within cryptographic algorithms to convert plaintext into ciphertext and back again. Similar to encryption, we have symmetric and asymmetric keys. Symmetric keys are identical and used for both encryption and decryption, while asymmetric keys consist of a pair of keys, a public one and a private one. These keys are mathematically related, meaning data encrypted with the public key can only be decrypted with the corresponding private key and vice versa. The strength and security of a cryptographic system are largely dependent on the complexity and secrecy of its keys. Longer keys generally provide stronger security because they are more resistant to brute force attacks. The next cryptographic concept that we'll discuss are hash functions. Hash functions are another component of cryptography, designed to take an input or message and return a fixed-size string of bytes, typically a hash value or digest, that appears random. The primary purpose of a hash function is to ensure data integrity by producing a unique output for every unique input. Even a small change in the input will result in a significantly different hash, a property known as the avalanche effect. Hash functions are deterministic, meaning the same input will always produce the same output. They are widely used in various applications, such as verifying the integrity of data, securing passwords through hashing, and enabling efficient data retrieval in databases. Common hash functions include MD5, SHA-1, and the SHA-2 family. The security of a hash function lies in its ability to resist collisions, where two different inputs produce the same output, and preimage attacks, where it is computationally infeasible to reverse engineer the original input from its hash. Now that we know a bit about encryption and hash functions, we can examine another cryptographic technique: digital signatures. Digital signatures are a fundamental technique used to authenticate the integrity and origin of digital messages or documents. Similar to handwritten signatures, digital signatures provide assurance that the content has not been altered and comes from a specific sender. The process begins with the sender creating a unique digital fingerprint of the message using a hash function. This hash value is then encrypted using the sender's private key, forming the digital signature. Upon receiving the message, the recipient uses the sender's public key to decrypt the signature and verify the hash value matches the message content. If the hash values match, it confirms the message's integrity and authenticity. Digital signatures are essential for secure electronic transactions, document authentication, and ensuring non-repudiation, where the sender cannot deny having sent the message. Widely adopted digital signature algorithms include RSA and DSA, digital signature algorithm, providing robust security against tampering and forgery in digital communications. Up next, we have certificate authorities. Certificate authorities, CAs, are trusted entities in the field of cryptography and digital security responsible for issuing and managing digital certificates. These certificates play a critical role in establishing trust on the Internet by verifying the identities of individuals, organizations, and devices. A digital certificate binds a public key with an identity, such as a person or an organization, and is used in secure communications like HTTPS. When a CA issues a certificate, it validates the identity of the requester through a rigorous verification process. This validation process ensures that the public key contained in the certificate genuinely belongs to the entity named in the certificate. Once issued, the certificate can be used to facilitate secure encrypted communication and authenticate the identity of the parties involved. CAs also maintain a certificate revocation list, CRL, to invalidate certificates that are no longer trustworthy. By providing a hierarchical trust model, CAs help maintain the integrity and security of digital interactions across the Internet, enabling users to trust websites, software, and email communications. Now let's look at SSL/TLS protocols. SSL, Secure Sockets Layer, and its successor TLS, Transport Layer Security, are cryptographic protocols designed to provide secure communication over a computer network. These protocols are essential for protecting data transmitted between a web server and a client, such as a user's web browser, ensuring the confidentiality, integrity, and authenticity of the data. SSL/TLS work by encrypting the data exchanged, making it unreadable to anyone who intercepts it. The process begins with a handshake, where the server and client exchange cryptographic keys and establish a secure session. This handshake involves the use of digital certificates issued by certificate authorities, CAs, to verify the server's identity. Once the secure connection is established, the data can be transmitted safely. SSL/TLS is widely used to secure web browsing, email communication, online transactions, and other forms of data transfer. The presence of HTTPS in a URL indicates that SSL/TLS is being used, providing users with confidence that their data is protected against eavesdropping and tampering. And lastly, let's look at public key infrastructure. Public key infrastructure, or PKI for short, is a comprehensive system that manages the creation, distribution, storage, and revocation of digital certificates. PKI is fundamental to ensuring secure communication and authentication over networks, particularly the Internet. At its core, PKI uses asymmetric encryption to establish trust between parties. It consists of several key components: certificate authorities, CAs, that issue digital certificates, registration authorities, RAs, that verify certificate requests, and entities such as individuals or organizations that hold the certificates and repositories that store and distribute certificates, and certificate revocation lists, CRLs. PKI enables secure digital transactions, email encryption, and ensures the authenticity of websites through protocols like SSL and TLS. By providing a framework for managing and verifying digital identities and encryption keys, PKI plays a crucial role in maintaining the integrity and confidentiality of electronic communications and transactions. In conclusion, understanding the basics of cryptography is essential in our increasingly digital world. We've covered most of the fundamental concepts related to it. All more sophisticated ideas are built upon these few concepts that we've discussed in this video. The importance of cryptography cannot be overstated, as it not only protects personal and organizational data from unauthorized access and cyber threats, but also fosters trust in digital interactions. As technology continues to evolve, the role of cryptography will remain vital in addressing emerging security challenges and maintaining the privacy and security of our digital lives. This concludes our exploration of the basics of cryptography. If you enjoyed it, consider subscribing to our channel and liking the video. Feel free to also check out our other videos on related topics. Thank you for watching.